now that we know what a tree is and what it can do, let's talk about how a tree is actually created. All of the data starts at that root node at the top of a tree. The second step in the algorithm for designing this tree is finding a single variable and a single location in that variable that divides the observations in the current location, or the root node in our example, into the best possible two subsets. So if we're talking about donations, is it ages where people who are over 20 do a certain thing a lot of the time and people who are under 20 do a certain thing? Is it incomes where people who make more than $300,000 do something very commonly and less than $300,000 do something different? So the question is, which variable will make the best possible two subsets? And for a second, let's just assume we know what that word best means. Once we've found how to create the best two subsets of data, divide the data into those two subsets. So if we find that it's income at $300,000, then just divide. Take all of the people who earn an income of over $300,000 and put them off to the side, and then take all the people that make less than that amount and put them in a different group, so that we've divided the data into two locations based on that single variable and that single location in that variable. And then we're just going to repeat in each child node. So for each of the two subsets we've created, let's just keep splitting. For each one, find the most meaningful, best way to divide those data sets into two more data sets. So essentially, we're creating distance between the observations in one group and the observations in the other group. And we're just going to repeat that until there are 5 or fewer observations in each group. So if there were only 5 people who made more than $300,000, we might still split on that, but we're not going to split anymore. We're finished. So we will only split on the people that made less. So we're going to stop whenever there are 5 items or observations or days or whatever our units are in our data set. We're going to stop when there's 5 of those or fewer in our node. When we have 5 or fewer items, the average response is going to be what our response is, our predicted value for that node. So if we have 5 items and most of those are yeses, then we're going to say that yes is the decision made here. If we have 5 items and we're predicting how many hours it takes to deliver packages, it'll be the average amount of time that it took to deliver the packages on those 5 days. That is the predicted value. But we've been skirting around this idea of how those divisions are identified. What is the best division of the data? So let's talk about how to find that best division. So let's consider an example in order to do that. So look at this little data set of 10 students. Grade 267 is this class. This is the experimental version, 267. And those are the average final grades for this class for 10 students. In the second column, UD 201, a 1 means that they took Math 201 at the University of Delaware, and a 0 means they did not. The third column, Math Friendly, is an indicator of how much the student likes math, a 10 being, I love math, it's exciting for me. And grade 201 in the last column is the grade they earned in their Math 201 class, no matter where they took it. So we're going to try to create a decision tree for this data that best predicts the grade they get in this class, because that's what I'm most interested in. I want to understand student performance in this class. So we need to start by understanding total variation, because I told you we want to create distance between observations so that we can predict them best. So we have to understand, what is the total variation? What is the total distance of this data set? How close together are the observations? So for variation, we're going to be looking at the average, which is 79.2 for this particular list of numbers. And we're going to calculate the total sum of squares. And we've seen this calculation before. It's part of the variance calculation. It's the sum of squared distances between each item and the mean. For this data set, that would mean taking 98 minus 79.2, which is the mean, and squaring it. and adding 44 minus 79.2 squared, and so on, for all 10 observations. And we'll get this number 2441.6. This is the total variation in the data set. So now when I divide the data into two groups, let's say on whether they took UD's Math 201 course, I want to reduce that total variation somehow. So all data, all those 10 students will start together, and I need to find the best variable to split on. So let's try one. Is it splitting on where they took their 201 class? Well, if they did not take their 201 class at UD, those 5 students have an average score in my class of 70.4 and a total variation in that data set of 1221.2. For the students who took Math 201 here at University of Delaware, they had an average score in my class of 88, and their variation was 446. Let's consider a different possible split. Now again, we're going to go back to all 10 observations because we're still just trying to locate the best split. We haven't actually split yet. What if we split on the grade from their 201 class? Did they score better than 85, worse than 85? If they did not score better than 85, so that's a no to the question grade greater than 85, then the average score in my class is a 69.6 and the variation is 1069.2. If they did score better than an 85 in 201, then the average grade in my class is an 88.5 with variation of 450.8. The best split creates the smallest total variation. So we add together the variation in the two groups and see just how small the new variation is. If we split on UD 201, then the total variation here is 1200 plus 440, so that's about 1660. If we split on the grade in 201, and specifically we're splitting at a grade of 85%, then we'll get about 1000 plus about 450. That's going to give us about 1510. So the split between the two of these that gives us the smallest amount of total variation is this grade in the 201 class being better or worse than 85% for a final grade. So of these two choices, we prefer this one because when we look at those two groups, we've taken 10 observations and we've divided it into two groups. And the total variation across those two groups is now smaller because we're not taking the total sum of squares for everything with one mean. We're looking now at two different means, one for each group, and allowing each to vary amongst itself. So now we're calculating the total being the sum of the variation in each group amongst itself. So we want to find the split that creates the most distance between the two groups while reducing the variation inside of each group. Now R is going to consider every possible variable at every value every time it thinks about splitting a node. So it's not just considering did you take Math 201 here and grade 201 being better or worse than 85%. It's going to consider the grade being 86%, 84%, 42%. It's going to consider every possible split. It's also going to look at math friendly and factor that in and see if we should split on 3, 4, 5, and so on. So it's going to make all of those considerations, and this is just a small example. So when the tree is created, so many different calculations are happening. We're outsourcing the decision making of how to build the tree, how to build the best tree to R, and it's going to do it very quickly.